Hello friends, today's lecture we're going to talk about retaining structures and of course lateral earth pressure subject, as you remember from soil mechanics course. Actually, in foundation engineering lecture, lateral earth pressure subject will be applied to design of retaining structures. Then let us start with Rankine's theory of earth pressure and how this theory will be applied for design of retaining structures. As you know from soil mechanics course, Rankine's earth pressure theory considers the state of stress in a soil mass when the condition of plastic equilibrium has been reached. Due to what? Due to stress state change in the field. When shear failure is on the point of occurring throughout the mass, not on one single plane, throughout the mass. This theory satisfies the condition of a lower bound plasticity solution. The Mohr circle representing the state of stress at failure in two-dimensional element is shown in this figure. The relevant shear strength parameters as shown here, cohesion and internal friction angle. Shear failure occurs along the plane at an angle 45 plus pi over 2. 45 plus pi over 2. This angle equals to failure angle in the field. Let us consider a semi-infinite mass of soil with a horizontal surface and having a vertical boundary formed by a smooth wall. And this soil here behind this wall is assumed to be homogeneous and isotropic. Of course, as you know, these two conditions located at depth Z is subjected to a vertical stress sigma Z, vertical stress, and horizontal stress sigma X. Then, since there can be no lateral transfer of weight if the surface is horizontal, actually this is the simple case. In actual surface is generally sloped, but it's just a starting point, it's a simple case. No shear stress exists on horizontal and vertical planes. Therefore, these two stresses, sigma X and sigma Z, without shear stress, of course, these two are principal stress. And of course, sigma Z is maximum principal stress, and sigma X will be, in this case, minimum principal stress, sigma 1 and sigma 3. And please focus on this wall. If there's a moment on the wall away from the soil, left side, away from the soil, to left. The values of this stress, sigma is sigma z, how again these two stress will change. Actually, when this wall move away from the soil, of course, lateral stress in horizontal direction, or sigma x, should decrease. Because soil here will expand laterally. And what about sigma z? Sigma z doesn't change actually, because sigma z depends on this thickness z. Because unit weight and z doesn't change, sigma z will stay constant, doesn't change. So, in Rankine theory, this state, when wall moves along away from the soil and sigma x decreases, this state is called active case. Let us discuss reverse. When this wall moves into the soil, right side. So, soil here will be compressed in x direction. So, sigma x will be increased. And then this case is called passive case in Rankine theory. In the field, in active Rankine state, the angle of failure zones will be theta, and the maximum stress will be along this way, and the failure zones, imaginary failure planes, are as shown. In passive case, because the maximum stress will be along x direction, and principal stress trajectory will be changed, overturned 90 degrees, and failure planes will be as shown in this figure. Let us discuss this issue on more circles. And let us start with active case. In active case, movement is away from the soil. And this is our stress state without movement, or in other words, in rest condition or at rest condition, this green circle. When we move this wall away from the soil, so soil in x direction will expand and sigma x will decrease from this value along this way in negative side. Failure will occur when new circles, reduced circles, touch to our failure envelope. So this state shows failure time. Decreased sigma x reached to this value, and new circle is tangent now to failure envelope, and active shear failure planes will be mobilized. In passive case, this is again our stress state at rest. This is at rest condition, the same as in this figure. But in this case, sigma x will not decrease, instead will increase. So when sigma x increases to this value, our new circle will touch the failure plane, and this is time of failure, and failure will be mobilized along this failure zones. And the failure surface degrees, slopes, can be obtained just coinciding pole point to failure plane, and this will be equal to 45 plus 5/2. Similarly, and of course we can state this condition in an equation. The earth pressure here is called Ka, active earth pressure. And we can express Ka whether this case or in this form. A similar case for passive condition, pole point intersect with failure point. This is the failure angle, 45 minus 5/2. And now the coefficient is Kp, passive earth pressure condition. You can express this way or this way. Okay. The horizontal stress for the active case is defined as the active pressure, Pa. And it's directly to the self-weight, due to self-weight of the soil. This equation is defined as the active pressure coefficient. When the horizontal stress becomes equal to the active pressure, so the soil is said to be in the active Rankine state, and the value can be calculated using this equation. On the other hand, if the wall is moved against the soil mass, this is the passive case, and due to compression, sigma x will increase. So sigma x becomes the maximum stress value and the major principal stress. Sigma 1, let me show here, yes. Sigma 1 in here is at the horizontal direction. But in the at rest condition, horizontal stress was minor principal stress. Due to this increase, major principal stress will be at horizontal direction. And this is Kp. And the pressure at the soil can be calculated using this way. Let me show only a cross section. The active and passive pressures increase linearly with depth. When cohesion is 0. Triangular distribution can be obtained as shown here, but please note that when cohesion is 0. when cohesion is not 0. So in this case, soil is called cohesive soil. The value of PA is 0 at particular depth. That's 0. And this triangular distribution will change to this distribution. Because cohesion try to hold this soil on its place due to cohesive strength. With P equals 0. This means that in the active case, the soil is in a state of tension between the surface and depth to Z0. Along this depth, the soil here will be stressed under tension. So this tension cannot be relied upon to act on the wall, since cracks are likely to develop within the tension zone, and a part of the pressure distribution diagram above Z0 here should be neglected. Because we know tensional strength of soil is negligible, and generally we can take as 0. When tensile strength here approximately 0 at negligible value, we can neglect this zone. We will consider only this zone. Actually, generally in the field along this zone, fractures or cracks are observed due to this low tensile strength of soil. The force per unit length of wall due to the active pressure distribution is referred as the total active thrust, as shown here, PA, for a vertical wall surface of H. Let me tell again, this zone is neglected. This is crack zone, crack depth. And this force, PA force, acts at a distance of one third of wall height. But as we know, this zone doesn't contribute to strength. So we will consider only this depth, and application of PA will be 1/3 of H minus Z0. Let us apply the same thing to passive case. The force due to the passive pressure distribution is referred to as the total passive resistance, PP, for a vertical wall surface of this height, and can be calculated using this equation. First component is from this triangular distribution, and the second component is due to cohesion. But here, in this case, the sign is positive, but here, sign is negative. Here is subtracted, but in passive case, the sign is positive. The two components of PP have different distribution. The first component is triangular distribution, and the second component is rectangular distribution. And the application points of these two components are different. At rectangular component, the application point is 1/2 of h. In triangular component, it's 1/3 of h. So combination of these two components will be around here, between these two levels. If a uniformly distributed surcharge pressure of Q, as shown here, acts over an entire surface of the soil mass, the vertical stress sigma z at any depth is increased to gamma z. This is the stress due to the soil proportional to depth plus Q plus this new stress, resulting in an additional pressure of KAQ in the active case or KPQ in the passive case. Both distributions being constant with depth, as shown in this figure, and this distribution is rectangular for both cases. The surcharge concept can be used to obtain the pressure distribution in stratified soil deposits. Of course, we know soil is layered and not homogeneous generally. In the case of two layers of soil having different shear strength, the weight of the upper layer can be considered as a surcharge acting on the lower layer. If the soil below the water table is in the fully drained condition, the active and passive pressures must be expressed in terms of the effective weight of the soil and the effective stress parameters C prime, phi prime, effective cohesion and effective internal friction angle. For example, if the water table is at the surface and if no seepage is taking place, the active pressure at depth Z can be given by this equation. Please note that internal cohesion, internal friction angle, and unit weight are shown as prime. Corresponding equations apply in the passive case. The hydrostatic pressure gamma Wz due to the water in the soil pores must be considered in addition to the active or passive pressure. For the undrained condition in a fully saturated clay, the active and passive pressures are calculated using undrained shear strength. Undrained shear strength. What does it mean? This is cohesion when internal friction angle is 0. Undrained shear strength, undrained cohesion, and unit weight in calculations will be gamma saturated. Remember from soil mechanics, water in the soil pores saturated. all the volume occupied by water. In the Rankine theory, it's assumed that the wall surface is smooth, whereas in practice considerable friction may be developed between the wall and the adjacent soil depending on the wall material, but in this theory it's neglected. When soil is sloped, as in general, it's assumed that the active and passive pressures act in a direction parallel to the sloping surface, as shown here and here. Consider a rhombic element of soil. Rhombic element in Turkish baklava. A rhombic element of a soil with sides with vertical and at an angle beta to the horizontal at depth z in a semi-infinite mass. The vertical stress and the active or passive pressure are each inclined at beta to the upper face sides of the element. Since these stresses are not normal to their respective planes, I mean, there are shear components, they are not principal stresses now. This is important. In the active case, the vertical stress at depth z on a plane inclined at an angle beta to the horizontal is given by this equation, not just gamma z multiplied by cosine beta. And in active and passive case, active and passive earth pressure coefficients and active passive stresses should be modified using this angle beta. And let us talk about earth pressure at rest. At rest means no positive or negative change due to an engineering activity. Soil rests as it was. If the lateral strain in the soil is zero, no active or no passive pressure, this line, no expansion and no compression. And the state of stress is called pressure at rest and usually expressed in terms of effective stress by this equation K0 here. This is coefficient of earth pressure, but coefficient of earth pressure at rest. 0 means at rest, and K0 coefficient of earth pressure at rest. The relationship between strain and lateral pressure coefficient depends on the initial value of K0 and on whether excavation or backfilling involved in construction. The strain required to mobilize the passive pressure is considerably greater than that required to mobilize the active pressure for normally consolidated soils. The value of K0 can be related to the effective stress parameter phi prime by this following equation. K0 equals to 1 minus sine phi. Let me express in this figure again. This is at rest condition when this wall move away from the soil. So this is active case, and coefficient of earth is called coefficient of active earth pressure, this value. And in reverse case, K value will reach to Kp. And K0 will be between Ka and Kp. For overconsolidated soils, the value of K0 depends on the stress history, and stress history can be defined by overconsolidation ratio. A typical relationship between K0 and OCR, overconsolidation ratio, for a clay determined in triaxial test is shown in figure. I'm sorry for my allergy. And for typical values of K0 for different soils are shown in this table. Let us solve one example. Example 12.1 for the retaining wall shown here. We will determine lateral earth force at rest per unit length of the wall. And also we will determine location of resultant force. Assume that it's normally consolidated soil, OCR1, normal consolidated soil. Soil parameters are given below groundwater table and above groundwater table. Above the groundwater table, starting from the surface, lateral stress will increase down to depth, down to a groundwater table, and below groundwater table, the stress which calculated for the first stratum will continue as rectangular distribution, as shown here, and stress due to the unit weight of second stratum again will increase in triangular distribution. Let us start with calculation of K0 at rest condition, because the question asks at rest condition. K0 1 minus sine phi, because the soil is normal consolidated soil, we can use this equation, and K0 is 0.5. At rest, at the surface, the stress will start with 0, of course. At this depth down to groundwater table, at that 2.5, let us calculate vertical stress, 16.5. This is unit weight multiplied by depth. So this is stress. Soil stress. Multiplied with K0. Now this is horizontal stress. We can put here 263. And for the second layer, down to depth 5 meters, The first stress due to the first layer will continue as rectangular distribution, this component, and stress due to second layer will be affected by groundwater table because it's under the groundwater table. So 19.3 minus unit weight of groundwater comes from this relationship, and multiplying with K0, this equation will give us sigma H at depth 5 meters, 3249. And this distribution is for pore pressure. Pore pressure starts with groundwater table and increase proportional with depth. From Z0 to Z2.5, because no groundwater exists here, pore pressure is 0. Under the groundwater table, down to 5 meters, pore pressure will increase to 24.53. The pressure distribution for the wall, total both total stress and effective pore pressure, is shown in this figure. So total force per unit length means the dimension perpendicular to screen, perpendicular to paper plane. P0 will be summation of this four area 1, area 2, area 3, area 4, and the location of center of pressure measured from the bottom of the wall can be calculated using this equation, and Z bar is 1.53 meters. We have one more example. A 6 meter high retaining wall is to support a soil with unit weight gamma 17.4 kilonewton per cubic meter. Soil friction angle is 26 degrees and effective cohesion is 14.36 kilopascal. And we will determine the Rankine active force per unit length of the wall, both before and after the tensile crack occurs, and determine the line of action of the resultant in both cases. Let us start with active earth pressure coefficient. For internal friction angle 26, just putting 26 here, Ka is 0.39, and just putting this sigma A equation, this is square root of Ka, and at depth Z0, at the surface. Because h is 0, the first component will cancel out. We'll have only this component, but having minus degree. Minus degree means is a minus sign, I'm sorry, means the soil down to this depth will be under tension. The value is 17.95. And this tensional stress will result in crack behind the wall. And at depth, that's 6 meters. 6 meters. Sigma A prime will be equal to 22.77. Just putting this Ka value here. But at depth Z, because we have H now, H not 0, putting 6 meters here, the result is positive at depth 6 meters. Active force before and after the tensile strength. What does it mean? Before tensile crack appeared means PA will be equal to 1/2 gamma H squared Ka minus 2Ch square root Ka, and is equal to 14.46 kilonewton per meter of the wall. The line of action of the resultants can be determined by taking the moment of the area of the pressure diagrams about the bottom of the wall. Taking moment, Z can be calculated, and Z bar, depth of crack, is 5.45 meters. Here minus means under the surface. Active force after tensile crack appeared. Let us start with that value, depth of crack. Depth of crack means is stress. Let me show here. Yes. Stress is 0. Stress is 0. And we can calculate this depth. Because the stress is 0, that will be equal to 2C over gamma square root of Ka, and the value can be calculated as 2.64. And using equation 11, just putting the values here, we just calculated Z sub C, and PA is 38.25. Figure 12.6C indicates that the force PA, 38.25 kilonewton per meter, is the area of the hatched triangle. Hence, the line of action of the resultant will be located at a height of Z bar, and of course this Z sub C will be neglected, and our Z, considered Z, will be equal to H minus Z sub C, and one third of this height is the location of resultant. So location of resultant can be calculated as 1.12. And we can continue with chapter 13, retaining wall, and we will apply this earth pressure concept to design of retaining walls. Up to now, do you have any question? About earth pressure? Because I am passing to chapter 13. No question. Okay. Let us start to retaining walls. Retaining walls are structural units which are designed and manufactured to retain earth pressure. And can be classified into 4 gravity retaining walls, as shown in figure A, gravity retaining walls. These are constructed with plain concrete or stone masonry. They depend for the stability on their own weight, as the name refers, gravity retaining walls. The retaining mechanism comes from, or strength comes from its own weight. Semi-gravity walls, when a small amount of steel is used for the construction of gravity walls, such walls are referred to as semi-gravity walls, because here very limited reinforcements are used. Cantilever retaining walls made of reinforced concrete. As a result, the cross-section is smaller than gravity walls. And one other variety is counterfort retaining walls. Similar to cantilever walls, at regular intervals, they have thin vertical concrete slabs known as counterforts that tie the wall and the base slab together. The purpose is to reduce the shear and the bending moments. We have 2 steps in construction of retaining walls. First step is geotechnical. The second is structural. In geotechnical step, or in geotechnical phase, with the lateral earth pressure known, the structure as a whole is checked for the stability for overturning, sliding, and bearing capacity failures. In structural phase, each component of the structure is checked for strength and reinforcement. Of course, as you understand, in this lecture, we will consider only geotechnical phase, and the second phase will be discussed in structural engineering courses. And today I want to stop here, and next week we will further discuss application of lateral pressure theories to design of Earth's retaining walls. If you don't any question, I'm gonna stop here. No question. Okay. See you next week.